Now, we have two angles standing on the same arc of this circle. The arc runs from this point to this point here. We have the angle at the center of the circle. That's got by drawing a line from the center to this end of the arc and another line to the other end of the arc. In this case the angle is 101.58 degrees. Now the angle at the circle standing on the same arc would be this angle up here. We just pick any point on the circle and join it to the endpoints of the arc. So we could have this point anywhere. We could have chosen a point here or here, anywhere we like. And the theorem says that the angle at the center of the circle is twice the angle at the circle standing on the same arc. So in this example the angle at the center is 101.58, and that's actually 2 times 50.79. It's 2 times the angle at the circle. And we can move this around. You can see that that relationship always holds. So for example, if the angle is about, say, 140 degrees here, we see that the angle at the circle is half of this angle. Half of 140.38 is 70.19. Now the theorem is also true if we move this point, say, down to this position here. So we have a different picture. We see that the angle at the center is twice this angle. We are going to start by proving the theorem for this situation here, and later on we will prove it for this different looking situation here. We draw a line from the point on the circle here through the center, and we note this angle here which we call C. This angle C is an exterior angle of this triangle. Now this triangle here is an isosceles triangle because the distance from the center to this point is a radius. Similarly, the distance of the center to this point here is also a radius. So I have 2 ticks on each of these lines to indicate that they are radii, they have the same length. Well, in any isosceles triangle, the angles opposite the equal sides are equal. So the angle opposite this side is this angle down here, which I'm calling B, and the angle opposite this side is up here, which I'm calling A. So A equals B, as you can see, and of course moving this around won't make any difference. We can change those angles. Now, since C is an exterior angle of this triangle here on the left, it's equal to the sum of the 2 interior and opposite angles. So C must equal A plus B. But since angles A and B are the same, we can replace B with A, and we have C equals A plus A, which is 2A. So this angle here is twice this angle up here. Now in exactly the same way we could look at this second triangle here. This second triangle is also an isosceles triangle. The distance of the center to this point is equal to the distance of the center to this point here. So that means that the base angles, or the angles opposite the equal sides of this isosceles triangle, are equal. And of course the exterior angle, which is this angle here that I'm calling D, is the sum of the 2 interior and opposite angles. So we will end up showing that this angle D is twice angle E. So D equals 2E. That means that if we put D and C together, we get the angle at the center of the circle. That's what we had at the start. So D plus C is the same as just adding 2 times A plus 2 times E. But 2 times A plus 2 times E is 2 times A plus E. We can factorize out to 2. So we end up showing that the angle at the center, which is called D plus C in this case, just put these two together, equals 2 times the angle at the circle. The angle at the circle is A plus E. Now let's consider this case here. The angle at the center of the circle here is called A, so it stands on this arc down here, the arc joining this point to this point here. Angle B is an angle at the circle. We can get that by picking any point on the circle and joining the point to the endpoints of the arc. And it's also true that angle A is twice angle B. Angle A in this case is 68.68, so angle B would be 34.34 in this case. Now we prove this in a similar way to before. We take the point at the circle and we draw a line through the center of the circle. Obviously we get a different picture. Then we note that we have two isosceles triangles formed. One of them is this triangle here. I'll just try to highlight it here. So we have two equal sides because these two lines are both radii of the circle, and the angles opposite the two equal sides are equal angles. So this angle is C, I'm calling C, and this angle I'm calling D. So C is equal to D. Now we can consider the exterior angle of this triangle. That's what I'm calling angle E, and we know that the exterior angle of a triangle equals the sum of the two interior and opposite angles. So E must equal D plus C. But since D is equal to C, we can replace the C with D, and we get E equals D plus D, or E equals 2D. Now we have a second isosceles triangle. If I join this point to F and this point over here, this side equals this side here because they're both radii. So the angles opposite these two sides are the same. Now the angle opposite this side I'm calling F. Now what about the angle opposite this side? Well, it consists of two angles. Angle B, which we're interested in, and angle D, which we saw earlier. So the angle here is D plus B. It must equal this angle here, which is F. Now we also have an exterior angle of this triangle. Here's the exterior angle. It's made up of these two angles, A and E. So the exterior angle A plus E equals the sum of the two interior and opposite angles. So A plus E must equal this angle, which is D plus B, plus this angle here, which is F. And what we can do then is we can plug D plus B in for F. If we do that, we get A plus E equals D plus B plus D plus B. Well, that's 2D plus 2B. And finally, we know that E equals 2D, so we can subtract E from both sides, and we're left with what we're looking for. We've proven that the angle at the center, which is A, equals twice the angle at the circle, which is B.